In this lesson, we're going to look at the forms of a quadratic. Specifically, we're going to be looking at standard form, the vertex form, factored form, and graphing. And what we're going to do is explore what each form can tell us about any particular quadratic. We're going to go through two examples, and they're going to be fairly simple examples. Hopefully, after you see these examples, you'll start to see the connections between the standard, vertex, and factored forms, as well as the various pieces of information that we can gather from each form. When we get to graphing, we're going to utilize three important pieces of information to visualize our quadratics. So let's go ahead and get started. In our first example, we're going to be given a quadratic in factored form, and we're going to need to translate it or rewrite it in standard form. So consider this example: f of x equals x minus 4 times x minus 8. We call this the factored form because from this function we can use the zero product property, which says that if either one of these two binomials equals 0, the whole function will equal 0. So these can be solved fairly quickly, where we can note that x minus 4, if that were equal to 0, I can say that x equals 4 satisfies that equation. And same thing over here. If x minus 8 equals 0, then x equals 8. So if I plug 4 or 8 into this function, the function will equal 0. So one way to think about this real quick is to note off to the side, okay, if I plug in 4, I say my function equals 0. Similarly, if I plug in 8, my function equals 0. So right away we have two of our zeros of the quadratic, or what we would call the roots. So we can call them roots or zeros of a function. I'm going to keep those off to the side for now, and we'll come back to them and explore them a bit later. So let's consider our x minus 4, x minus 8 as a factored form and how we need to represent it in standard form. Well, standard form is just the descending order of degrees of our polynomial, where you take each of the terms and express them in a form like this: ax squared plus bx plus c. And the easiest way to get there from factored form is to simply multiply out or distribute our two binomials. So I'm going to go ahead and take x minus 4, x minus 8, keep f of x over here, and we're just going to multiply this out. So we take our first terms, x times x is x squared, take our first and last terms, that's going to be negative 8x, take our middle terms, negative 4x, and our last terms. Negative times a negative would be positive 32. Let's go ahead and combine our middle terms, and we get x squared minus 12x plus 32. And as we see, our form matches the form given by the standard form above, right here, our standard form. Let's go ahead and box this off so we recognize this throughout. This is our standard form. We see our a in this case would be 1, our b value would be negative 12, and our c value would be 32. So we pulled some extra information here, right? We looked at the roots and the zeros because it was so readily available. But don't lose sight that all the work we did to translate from factored form to standard form was just the distributive property. We just multiplied out these two binomials, simplified that middle term, and we got our end result in standard form. Next up, we're going to take a look at what the axis of symmetry is and the vertex as we start to move into our vertex form. So when looking at the vertex and the axis of symmetry, it is often helpful to compare both the algebra and the geometric representation of both of those ideas, where we can visualize the vertex on the graph as well as on paper, right, in our equations. Since we already have kind of an intuitive understanding of the vertex and the axis of symmetry, I'm going to wait until the graphing portion to show you the visuals. Instead, I'm going to stick strictly to the algebra to show you what you need to focus on and how to interpret it. So let's continue using our example where f of x is equal to x squared minus 12x plus 32. And the vertex formula is very straightforward. It's given to us as the coordinate of negative b over 2a, and then that same point evaluated in our function, f of negative b over 2a. So we use this negative b over 2a to find the location of the vertex, and then we use this value here to determine what is the vertex, or what you can consider to be the height of your vertex, or the extrema. Oftentimes you'll hear the term extrema, or it'll be written as the extremes, right? The extremes of your quadratic. This is two ideas. It's either going to be a maximum or a minimum. Collectively, we just call those extremes or extrema on a function, right? What's the extreme value that we're concerned about when it comes to our function? It's either going to have a maximum or a minimum. So in this example, what is the vertex? What is the vertex? Okay. Given this form, right, ax squared plus bx plus c, our standard form, we can extract the b value and the a value in our vertex formula. So for negative b over 2a, we can say from our values, okay, negative 12 is the b value over 2 times a. A is 1 in this case. So we have positive 12 over 2, or 6. 6, as I said before, is the location, or the x value, right? This is our x value. And we need to determine the y value to determine what the actual extrema is. So we take 6 and we can plug it back into our function. So f of 6, remember, this is a function. We can always input a value to determine its output. F of 6 equals 6 squared minus 12 times 6 plus 32. So we can multiply this out. This is 36 minus 72 plus 32. From here, we just simplify. Negative 36 plus 32, that gives us negative 4. So the vertex occurs at a coordinate, so we need 2 points. We know negative 4 is the height, but what was the x value? Well, that was the input. Remember, it's 6. It's the value we started with. So we have a vertex that occurs at 6, negative 4. One other idea to add to this conversation is the axis of symmetry. So the axis of symmetry, it's considered to be the dividing line, right, where this symmetry occurs. And we represent vertical lines as x equals equations. In this case, we just take the x component of our vertex, and we say that the axis of symmetry for this quadratic occurs at x equals 6. That's all there is to the axis of symmetry. We know down the line x equals 6, which is at the point where x equals 6, right? All of the points on our graph where x equals 6. You can consider this to be our origin, right? X equals 6 here. This line, this vertical line, is our axis of symmetry where some quadratic is formed, however that may look. So next up, we're going to go ahead and represent this function in vertex form and show you how easy it is to represent it in standard form. For starters, what exactly is vertex form? Well, this is a function, a quadratic specifically, of the form a times x minus h squared plus k. From this, we can gather several pieces of information. A just tells us kind of the magnitude of our quadratic, right? Whether it's a really tight quadratic or if it's a bit wider, right? Just as a quick visual, right? It kind of tells us what's its magnitude, how small is that grouping or how wide is that grouping. Okay. The x minus h portion talks about the x value, specifically the x value of the vertex, and we represent it as h. Take note of that negative in here. This negative is about the form of this vertex form, not the h value itself. So sometimes we have to be careful with that and watch our negatives. And then the k value represents the k component of our vertex. So, as the name suggests, the vertex form when written correctly, tells us exactly what the vertex is. Okay, so if you recall from our previous example, we determined that the vertex was equal to 6, -4. So we're going to use this to define our vertex form of the quadratic. In this case, our leading coefficient was 1, so our a value is going to be 1 here. And then we go ahead and write x minus our x value of the vertex, which is 6 squared, plus k, so plus -4. I specifically wrote in these parentheses just to make sure I didn't mess up my negatives. So we're going to go ahead and simplify this to see how this looks without all the kind of extra features that help us, with our negatives. And what we see is our f of x vertex form is just x minus 6 quantity squared minus 4. Okay, from this I can extract several pieces of information. The magnitude is 1. Right, the magnitude, the a value in front is just 1. That just represents that we're dealing with a fairly normal or fairly standard quadratic. And the vertex occurs at 6, -4. This specific example is meant to cover how do we translate from vertex form to standard form. And all we have to do here is, like the previous example, we just need to multiply out our binomial. So what is the binomial in this case? Well, it's x minus 6 squared. Remember, this can be written as x minus 6 times x minus 6 minus 4. I'm going to go ahead and multiply all of this out, and we get x squared for our first terms, minus 6x for the outer terms, minus 6x for the inner terms, plus 36 for the last terms, minus 4. So we can simplify this to x squared minus 12x plus 32. And if you recall, only a few minutes ago, we just had our standard form, and this was the standard form of this quadratic. So you see, all we need to do, all the work we need to do to translate from vertex form to standard form is multiply out this vertex portion, this x minus 6 squared, the quadratic portion, right? That squared portion, multiply it out and simplify. And then we end up in our standard form. Standard form. Okay, so take some time, kind of visualize what a vertex form looks like, what a standard form looks like, and what path we need to use to get from one form to the other. In our next example, we're going to go ahead and take a look at how to translate or how to convert from standard form back into the vertex form. This is definitely the most challenging of the three forms so far, right? It's going to require a bit more work than just distributing out our vertex form or distributing out our factored form. What we're going to need to use is that completing the square method that we've learned along the way. We'll do a quick review because the process is fairly quick to handle, and it's just applying that technique correctly will get us into our vertex form. So how do we rewrite our quadratic from standard form to vertex form? If you recall, our example is f of x equals x squared minus 12x plus 32. And the vertex form that we're aiming for is of the form f of x equals x minus 6, that quantity squared, minus 4. We're looking to convert from this standard form to this vertex form. And as I mentioned, the way we accomplish this is using something called completing the square. So completing the square. And the way we accomplish this is using b over 2 squared. As a quick example of what it means to complete the square, consider the example we have when x squared plus 12x plus 36. With some factoring techniques, we can determine that this is equal to x plus 6 times x plus 6, which is equal to x plus 6 squared. So if I were to take the square root of x squared plus 12x plus 36, take the square root, I can determine that this is equal to just x plus 6. By perfect square, I mean I can take note that this thing can factor into something that multiplies by itself. In this case, it's x plus 6. Okay. Same way that if I had 81 and I wanted to determine its square, I know it has a perfect square of 9. So what we're looking for are these perfect squares to where I can factor this thing out into a nice expression like this. Okay. If I can factor this into x plus 6 squared, already we can take note it's starting to look like our vertex form. So how do we do that in this case? Well, it revolves specifically around our c value. We need to get our c value into a position that it makes this whole trinomial a perfect square. And we're going to use b over 2 squared to determine what this c value should equal. So in this case, b over 2 squared would be negative 12 over 2 squared, which is negative 6 squared, or 36. So I want my c value, we want c to equal 36. So the way we're going to express this is x squared minus 12x plus 36. See how I'm just injecting my c value to where I want it to be? The problem with that is this function has to remain equal. If I just change this number to 36, they're not the same function anymore. So what I'm going to do, I'm going to add my 32 here to make note that 32 is still part of the original function, and then I'm going to subtract 36. So you see these two values would technically cancel out, but I can make use of 36 here to complete the square. So we need to add 36, subtract 36, so that we haven't changed the actual value of our function. So from here, I'm going to simplify this a little bit. We still have x squared minus 12x. And remember, we want this plus 36 part. This is the c value that we're looking to complete the square. Then we have minus 4. I just simplified these two terms. So this is supposed to be a perfect square, and we can take note that, yes, if we take x minus 6 times x minus 6, this is the factored form of x squared minus 12x plus 36, with our minus 4 on the end. Let's go ahead and condense our x minus 6 terms. Squared minus 4. Let's put our f of x in front and check. And yes, we see f of x equals x squared minus 6 squared minus 4. That's the form we're looking for. Okay, so to recap this, what we specifically identified was this c value, this value on the end. We're looking to identify this value here that completes the square of our quadratic. The part that we need to get a handle on and watch carefully is how we manipulate our values on the end. Okay, we need to make sure this function does not change in value by adding 36 and throwing the whole thing out of balance. So we add 36, subtract 36 on the tail end, and then that gives us this minus 4 part, keeping this whole function in balance and completing the square. We now have a vertex form. So given standard form, I now have a vertex form to very quickly identify that 6, negative 4 is the vertex. Lastly, we're going to go ahead and run through another example, more quickly this time, where we're going to look at all the different components. How do I go from factored to standard? How do I go from vertex to standard and standard back to vertex? And then with all of that information, we're going to go ahead and graph a function. In this final example, we're going to start with a function in factored form, and it's going to be x minus 6 times x minus 2. Okay, so first thing we do is we make note this is our factored form, or factor form. And the reason we call it our factor form, it's because we have all the factors of our quadratic, and we can easily identify the zeros of our function, right? We see there's a 0 at x equals 6 and a 0 at x equals 2. That is at the points 6, 0 and 2, 0. From here, we're going to go ahead and represent the function in standard form. And the way we get it into standard form is by distributing out all of our values here, right? We're going to distribute and multiply. So let's go ahead and do that. First, outer, inner, last. we get x squared minus 2x minus 6x plus 12. If we simplify, we get x squared minus 8x plus 12. This is our standard form. Standard form. Okay, so the process to go from factored to standard form is fairly straightforward. We just multiply it out. But what information can we get from standard form relatively quickly? Well, when we want to graph this thing, it's also helpful to know where our function crosses the y-axis. And it crosses the y-axis when x is equal to 0. So I'm going to input 0 here, and I get 0 squared minus 8 times 0 plus 12, which is equal to 12. So there's a y-intercept at the point 0, 12. The next step along the way is to convert standard form into vertex form. Now I can use the vertex formula, negative b over 2a, to extract the vertex that way, but I'm going to go ahead and show you how to represent standard form in vertex form so that we can easily see the vertex as well as the technique used to move from standard to vertex form. So let's first start with f of x equal to x squared minus 8x plus 12. Remember, we need to use the completing the square technique here. And so in order to complete the square, we're going to use b over 2 squared. In this example, that's negative 8 over 2 squared, which is negative 4 squared, or 16. So I'm going to add 16 in, and then remember to subtract it so I don't change the actual value of my function. So we see f of x equals x squared minus 8x. I'm going to add 16 in here, plus 12 minus 16. So I'm going to add 16 because that's the value needed to complete the square. And then I have to subtract 16 on the end to make sure this portion balances out correctly. So we have two components here. We have f of x equals, the perfect square here is x minus 4 squared. And then I need to add this tail end, which is a negative 4. So by completing the square, I get my vertex form. And again, the reason we call it the vertex form is because we can easily identify what the vertex is. In this case, the vertex is made up of two components, the h and the k component, h, k. And watching our negative on the h portion, I can identify my vertex is 4, negative 4. And that's how we can represent from factored form to standard form to vertex form, the three major forms of a quadratic. Now the last little step here, just to highlight, that got a bit excessive. So our vertex, I'll write off to the side here, is equal to 4, negative 4. Now the last little step here that I can do just to demonstrate how to move from vertex form to standard form is to multiply this whole thing out. So if we take f of x equal to x minus 4 squared minus 4, and I multiply this out, that's x minus 4 times x minus 4 minus 4. So this multiplies out to x squared minus 4x minus 4x plus 16 minus 4, which simplifies to x squared minus 8x plus 12. And that was the result we had from our standard form up here in step 2. So the major techniques you want to look for are moving from factored form to standard form to vertex form, and how to move kind of backwards as well. How do I go from vertex form into standard form into factored form? This is just a matter of factoring. We've covered plenty of factoring before, so you know that. And what we're going to do on the next page is take the x-intercepts, the y-intercepts, and the vertex, and then represent this quadratic as a graph. So let's go ahead and write out the different components we have and that are needed to graph this function. if you recall, we had x-intercepts, or the zeros of our function, at 6, 2, and 2, 0. Then we also have the y-intercept that we solved for using the standard form at 0, 12. And lastly, we had from the vertex form the vertex itself, the vertex, at 4, -4. So let's go ahead and put these as markers on our graph so that we know where to point this thing. So we have 4, -4 for the vertex. That's +4, -4. So right here, we have a vertex. We have a y-intercept all the way up at +12. Now, because of the nature of this graph, it's going to be hard to demonstrate that, so I'm just going to kind of use this as a rough guide point. We have x-intercepts at 6, 0, and 2, 0. I'm going to put those in green at 6, 0, and 2, 0, here and here. And then you see, effectively, what we would need to do is draw this graph so that it starts at the vertex, travels up, up, up through this value, and also the same way here. We need to go starting here, travel up, 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 up. I'm kind of losing it a bit. Let's see if I have to take this in shorter sweeps. All right, something like this. And somewhere way up north, a bit off this graph, right through 12, that's where I would connect my graph. Okay, so very rough sketch here, but what's important is that we make sure we land on the important markers here. We have the vertex down here in red. We have the x-intercepts in green, and then we have the y-intercept here in blue. Okay, we need to cross through a y-intercept somewhere, and through, in this case, 2 x-intercepts, and down here we have our vertex. So these are the components we need to identify when we're graphing a quadratic. And as one final example, just to give you a much cleaner picture now that we've already graphed the vertex, x-intercepts, and y-intercept, is to show you what this would actually look like with something a little more dynamic. So this is the Desmos graph of this function. And I can bring it up here on the side, x squared minus 8x plus 12. I plop that function down, and then I can go ahead and look at the different components. So we see here there's a vertex at 4, -4. We have x-intercepts at 2, 0, and 6, 0. And then way up here at the top, we have a y-intercept at 0, 12. So taking the full picture, right, you can see it crosses here at 0, 12. We have x-intercepts at 2 and 6, and then we have a vertex at 4, -4. Those are the 4 features that we're looking for when graphing a quadratic.